So Robin had this problem, and I'm going to explain to her, but I'll show you how I handle it. Um, so the two things. So Robin was doing the histogram, which was good. Everything was fine there. The only thing I told you to do was if you copy these ranges. So if I do Control C and I paste them into there, what it does that where you change the numbers here, the actual data that was used in the histogram was in this column. So you need to show the ranges here instead of over there. And you'll notice, so before it was using these numbers, you changed them, but you changed them in the wrong place. So by moving these numbers over here, then it corrected the numbers on your graph. Okay. I think I also deleted the legend. So if you go to your graph and you edit it, and you go down to legend, none. Yeah, so you don't really need a legend because it's more, okay. So that was the only thing on the histogram. The problem you had was this descriptive statistics. And yeah, you got all that mess. Okay, so what I was going to do first was just delete all you did. We'll start fresh again. So so to do the descriptive statistics, you go to Tools, Add-ons, sorry, Start. And you wait, and you wait. Let's try it again. Start. Okay. So there's your descriptive. So you go to descriptive statistics. So with descriptive statistics, you have to specify your input range, and I think that one went okay. If you scroll down to the bottom, you'll see it goes all the way down to 240. So if I click in the cell here, it's actually going to put where my cursor is. So if I just backspace and I do A1 colon A240, then that should work. Okay. Now, as far as the output range, that's where the problem ended up happening. Also, so we're going to get rid of this and get rid of that and get rid of that. And so if I say OK, let's see what happens. Oh, anyway, so I just manually, I think for some reason it was highlighting this row, and so it was redoing it for every data point in the whole list. Yeah, so you just want one result. You got a bazillion results. So the best thing I found was just to manually input the ranges instead of, so whatever it pops up, just ignore that and then type in the actual ranges. And then again, the same for the output. What had happened was, I think it had highlighted this entire row somehow or another, and when you clicked in there, it did something like that. And so when you pushed return, you got a whole bunch of results. So just make sure that there's only one cell entered here, and just manually enter it in there. Okay, so that's all there was to it. Otherwise, everything looked good. And the one I sent you was with the corrections on it, so you could see what you're trying to get. Okay, so let's go to section 5. So we pretty much finished everything in sections 5. Let's see. So the whole idea here was for a population we had a mean and a standard deviation. And then using that population information, we could then calculate the probability of randomly picking a sample and knowing what the probability of that sample having a value. Okay. I just got like 6 messages in a row. It's like, what is going on here? It's about a meeting, so. Okay, so, or we could talk about what percentage of the data was between two values. So we did a couple examples. The only problems that we didn't work through was this one that's part of your assignment, so we'll look at that. And then we'll look at a few more examples that are in the book. So problems 58 through something, it gives you the mean and the standard deviation. And it says follow the methods of example 6 and find the data values corresponding to the following values of z. So you're basically going to make a sketch with the normal distribution on there, figure out where this point is, and do it in terms of z and not in terms of the variable. And then all you have to do is use the definition of the z-score to solve for the unknown value. So let's do that. So again, let's draw a picture. And because we're talking about z-score, I'm going to draw, well, we're going to draw it two ways. We're going to draw it with respect to z-score, and then we're going to do it with respect to the actual variable. So what they're talking about is the z-score of negative 2.39. Now if we do the same kind of plot, but do it in terms of the variable, yeah, that's the messages I keep getting. Let me close my email down so I can stop getting all these messages. Okay. So when we actually use the variable, I have to offset that a little bit. Okay. So in terms of the variable, it looks like this, where the mean is 76.8. So, the mean corresponds to the z-score of 0. So this negative 2.39 is somewhere over here. It's going to have a value. That's what we're trying to solve for. What is the value corresponding to a z-score of negative 2.39? So what we'll do is we will okay, what are we going to do here? Actually, I don't even know if we don't even have to use the tables, I don't think, to solve this problem. So let's write, what is the definition of z-score? It's equal to the value of the variable minus the mean divided by the standard deviation. And if I just check off what I know so far in this problem, I know the mean, I know the standard deviation, and I know z. So the reality is I don't have to use the tables at all. I just have to use the definition for z-score. And let me just algebraically solve it. You can use the solved equation instead of having to plug the numbers in. So the way you do this algebraically, because there are no numbers, they're all variables, is we would multiply both sides by s. So you'd get s times z is equal to x minus x mean. And then you would add x mean to both sides. So what we would get, these would cancel out, and you would solve for x. And on the left-hand side, you'd have the mean plus s times z. So that's all we have to do. So x is equal to the mean, which from the problem is 76.8, plus the standard deviation, which is given in the problem of 9.42, times the z-score, which is negative 2.39, and you just plug it in your calculator. So instead of being given the mean, the standard deviation, and the data point to calculate z, in this case they give you z, and you go the other direction. So you get 76.8 plus 9.42 times negative 2.39. And you get x is equal to 54.29. So this is a fairly extreme z-score. It's negative 2.39. There aren't that many data points that are between negative 2 standard deviations and negative 3 standard deviations relative to the mean. So now if we go to the next problem, we've got the same data, and actually I'm going to do something different. I'm going to use a different number that's even more extreme. Let's just say 1.26. So if I'm given a z-score of 1.26 with the mean equal to 76.8 and a standard deviation equal to 9.42, I just use the same equation, which says that the value is equal to the mean plus the standard deviation times z. And we have the same mean and we have the same standard deviation, but we now have a z-score of 1.26. So if we solve for z, or for x, we get 76.8 plus 9.42 times 1.26. And so that's the value associated with that z-score is 88.67. So just use that in your tool belt for going the other direction. It's just this definition for z-score solved for x, given the other three variables. Okay, I've got a list of problems that I'm going to choose from, and they're on another page. So that's the homework assignment. Let me find the page with my suggested problems. So I think it's here. There we go. Okay, so those are the example problems I'm going to do. I'm going to show you a graph here. This is, there's a lot of statistics around, and this was something that I think I found it last fall during the, when Trump was being elected or something like that. U.S. elections 2004. This is actually older data. Results listed by average IQ. There's a couple of interesting comments here. So I don't know where they got this data from, but it has states with the population average IQ, and they show who they voted for and their ranking. So we have Virginia. We're the 17. We have an average of 100, which is we have an IQ average of 100, which makes us average. And then you go down to the bottom, and Mississippi has the lowest IQ, according to this data. And you can see that who they voted for. So they voted, pretty much what this is showing is that the states that have a higher IQ voted for Kerry, which is the Democrat, and the ones that voted for the Republican had the lowest IQ. So, okay. I'm just showing you the data. Now, George Bush got elected, so what does that say? He also got us into the Iraq War, so that's another. Anyway. Now, you'd see something like that, and you'd like, okay, before you accept anything, for me, everybody has bias as far as their belief system, and so I would tend to probably say, oh yeah, I agree with that because I tend to vote Democrat, and I think that's a smart thing to do from my perspective. So I would look at that and I wouldn't question the results. Now, if I saw something that didn't support my preconceived notions, then I would probably either dismiss it and say, "Oh, fake news," or mainstream media, or something like that, or Fox News, whoever you're trying to. Or what the smart thing to do is to actually look into how they got the data. Okay, you have to be like a consumer of goods, cars. You have to be a consumer of facts. So the most recent thing that is this Facebook, where they have this one company illegally got data about Facebook users, and then they looked at their profiles and all the data, and they said, "Oh, this is most likely is a Trump voter. So we're going to target information to these voters to get them to be excited about Trump and go out to vote for him." And so you would send, these people would send stuff, and maybe they're true, maybe they're not true. So the question is, if you are a voter, say you're a Trump supporter, which is nothing wrong with that, then you get sent some information, and you're like, yeah, I agree with that because that supports my position of voting for Trump, or if it was Clinton the other way around, without any kind of questioning of the data. And it doesn't really matter what your political spectrum is. You should view anything that you hear or see with skepticism. And if it doesn't, just because it supports your preconceived notions, you shouldn't accept it without questioning the source and figuring out whether it's true or not. So, that's probably one of the things an educated populace should do, or just anybody. I mean, everybody should do it. But you guys are taking college classes. You ought to, if you get one thing out of going to college, is don't believe anything you hear and check it out for yourself. What are the sources? How did they come up with these particular results? So, if you look, a lot of times they'll give you how they came up with this stuff. Then you could look up that. And you're like, I don't really have time to do that. Well, if you don't have time to do that, don't have time to believe anything you read either. Okay, if you can't question something, then I don't remember getting any. I never watched the ads on Facebook, so it's going to be useless for me. But I do get posts, and they probably looked at my profile and said, "There's no hope for this guy as far as voting for Trump." So we're not even going to spend time going to this guy. But if you think about in terms of the election, what some people will say, well, that didn't make the difference. That didn't make the difference. Well, why did they pay people to do it if they didn't think it was going to make a difference? If you have some political campaign paying somebody to do something, they think it's going to make a difference. So when everything makes some difference, you don't really know how much. And if you take a little bit of those small differences and add them up, then you can swing a few important states and somebody can get elected that maybe shouldn't be elected. So anyway, that's be smart. Question everything. If something sounds too good to be true, it is. Probably is. Okay. So let's find my list of problems that we're going to do. Just a few more. Okay, so let me find one in the book, and I'll kind of give you a summary of the problem, and then we'll see how we would solve it. Really, all we have to do is pretty much most of the time we're given the mean and the standard deviation, and then we're asked to answer some question about percent or probability. Okay, so we've 8. We've already done that one. 12. We've done that one already. Filling cereal boxes. We did that one. Okay, so here's one. Relates to milk. So it's a different one. So it's kind of like filling the cereal boxes. So we have a machine that fills quart milk cartons, and it's set to average 32.2 ounces. That's our target. And the standard deviation is equal to 1.2 ounces. And it says, what is the probability that X is going to be less than 32 ounces? So yeah, it's pretty much exactly like the cereal, but it's milk instead. And again, what you're going to do is, if you can have a certain small percentage that's going to be underweight and not have any problems with consumers, but if you consistently ship them something that half the time it's less than 32 ounces, then they're going to complain about it. So again, the best thing to do is to draw a picture of what's going on here. So we draw our standard normal distribution, and we draw a line straight down the middle, which is our mean. So we're targeting 32.2, and that's because we want to have more than half the people get more than they asked for. So 32 is going to be somewhere down here. It's going to be to the left. Again, you don't need to be super accurate. And so what the question is, what is the probability that the value is going to be less than 32? Well, less than is going to be to the left. So what we have to think about is, how do we find that area? Because the curves that we have been using, that I handed out the other day, relates to the mean. And because the normal curve is symmetric, the procedure you do on the left-hand side is the same as the procedure you do on the right-hand side. So if we can find the z-score associated with this data value, then we can find the area between here and here. And we don't need to use the table to answer this question, but we can also, let me move that out of the way, so we can figure that out once we have the z-score. And then we can go all the way down to include everything below the mean. That's the green area, and we know that's a half, so we don't have to use the table to calculate that. And if we subtract those two areas, what we end up with is the answer that we're trying to find. So this part is 0.5. We find the z-score associated with 32, so go ahead and calculate that. Remember, it's the data value minus the mean divided by the standard deviation. So we've got all the standard deviation in the problem was 1.2. The mean is 32.2. The data value is 32. So we get a z-score for that. And then we use the table. So hopefully you still have your table from the other day. So take that z-score and look up the area. And I don't think I brought any extra, but it does remind me that I do have some things to hand back to you, which I think includes your test. So while you're doing that calculation, I'm going to hand these things out. Oops, sorry. So at first I thought I'd lost the test, but I think, this is my 9th year teaching here. I think I've only lost something once. So that's pretty good. Unless you're that one person, of course. Then it's not so good. But so you'll get a negative z-score. So you'll then take the positive of that, look it up in your table, find the corresponding area, subtract that from 0.5, and that will give you the answer. And it should be, probably, I don't know, 20 or 30, I guess. I'm just guessing. Percent, or 0.2 to 0.3 maybe. Okay, there's some tests. If I think I'll. So if anybody gets kind of stuck on something with their project, just send me the spreadsheet in Excel form and let me look at it. I don't want you to be spending hours on some single problem that you can't figure out. So I don't want anybody coming in and saying, I'm so frustrated with this class, I hate it. You got plenty of time. If you start working on it early, you got plenty of time to let me help you out if you get stuck on something. A lot of times it turns out to be very simple, and you're like, oh, I wish I'd known that. Okay. So let's see what the z-score is here. It's 32 minus 32.2 divided by, what was the 1.2 ounces. So actually it's going to be higher than I thought. So you'll get negative 0.2 in the numerator divided negative 0.2 in the numerator divided by 1.2. You get a z-score of negative 0.17, and the area associated with a z equal to 0.17. Okay, so you take the positive is 0.067. Which, yeah, what I did, yeah, I rounded up. It was negative 0.16666, so I rounded up to 0.17. So you get 0.67. So 0.5 minus 0.067 is 0.433, or 43%. That would not be good, okay? So the way you would handle that is either you might be able to design the filling machine so that it has less standard deviation, so it doesn't have as much variety, not variety, but variation in its number, or you have to increase the target. So you could pick some value, 5%. So the last example we'll do is we'll go, let's say 10%, just to do something, because I think we did 5% the other day. So if we worked with the same problem, but we said, what target should we use to only have 10% lower than the target? I mean, lower than the advertised, lower than 32 ounces. We'll just put 32 ounces. So the way that's, again, it's kind of the same drawings, but we'll go ahead and just make it slightly different here. So we have our normal distribution, and what we want is that we want this area to be, so the area is 0.1. So if this area is 0.1, what is the area here? Yeah, because half of it's 0.5. So the blue area is going to be equal to 0.4. So now you take that area and you look up the corresponding z-score associated with that. It's going to be a negative. We'll look up positive and then we'll make it negative because it's to the left, so we know it's negative. So we go to our table and we go down the area columns. So it's the third area column. We start at 0.369 and we go down to 0.4. Instead of looking to the right, we look to the left. So the z-score associated with 0.4 is 1.28. But because we're to the left of the mean, we're going to use z equal to negative 1.28. So we got a z of negative 1.28. We've got a we don't know what the target is. We know that x is 32 because that's, what we're trying to find is what is the mean to get it so that when x is 32, the cutoff point for being at the target, and the standard deviation is given in the problem as 1.2 ounces. So this is kind of like the problem we just did. If we go back to that equation that I asked you to write down, it said that well, actually, I think it's the other way around. It'd be the same kind of thing. Using the definition of the z-score, let's just write that down. So the z-score is equal to x minus x mean over the standard deviation. So if you multiply both sides by s, you'll get z times s is equal to x minus x mean. And if you solve for the mean value, or what our target is going to be, is going to be equal to x plus, actually minus, I guess, if I solve for it. It'll be x minus the standard deviation times the z-score. So now all I have to do is plug in the numbers. The value is 32. That's where the cutoff is for my below 10%. My z-score is negative 1.28, but I subtract it, so I'll end up adding it ultimately. And well, that's the z-score. Let me switch it around since I have my equation. Standard deviation is 1.2 ounces. My z-score is negative 1.28. And so I get 32 minus 1.2 times negative 1.28, and I get 33.5 ounces. So instead of 32.2 ounces, I have to have a target of 33.5 ounces, so that with that target and this standard deviation, that only 10% of the cartons filled will be below the advertised price. So that's another way of kind of using the same table, just going in a different direction. For you guys, you'll just, the examples that you have on your assignment is what you'll be responsible for. I'm not going to give you all these different varieties. I just wanted to kind of demonstrate where you practically might use something like this. Okay, it'd be interesting. What if I'm thinking about if I was, I usually buy cereal. I go to Aldi's to buy my cereal because it's cheap at Aldi's. And but I usually buy like 5 or 6 boxes at a time because I have the same breakfast every morning, bran flakes with raisins. And so next time, maybe I'll buy 10 boxes. Then I could take I don't want to take all the cereal out and weigh it, but I guess if you assume the boxes weigh the same and the cereal weighed differently, you could just weigh the whole boxes and see what the variation was, and actually do the statistics and say, I actually bought the cereal, and see, here's the advertised. I could find what the weight of the box and the weight of the bag is, and then I could subtract that from the weight of the bag, box, and cereal to get the weight of the cereal. And then I could, so I don't have to eat a big pile of cereal at one time. And then, so next time I'll say to my wife, I said, I'm going to buy 20 boxes of cereal. She'll go, what? Are you crazy? Where are we going to put all this? Yeah, but it's for my math class. And then you could actually have some data. It would be interesting to see how that actually compared. It's tempting. 20 boxes, though, that'd be a lot of cereal. That might be a whole year's worth of cereal. Okay, so I've assigned the homework for section 5. So we're going to go into a new topic now. So one thing I showed last time was, I think I demonstrated how if you have a population of data and you take a small sample of it, how the sample histogram compared with what you would get if you looked at the large population. If you had a normal population, I'm not sure if I did that or not. I think I did this after your class, and I said I need to come up with a spreadsheet that demonstrate this better. So if this is a repeat, I apologize, but I don't want to. Okay, so I don't think I showed you this. So what I did was I took this data that I generated, and there's 1,000 data points. So it's a pretty big population, and I randomly select 25 data points out of those 1,000. That's my sample. And I created a histogram, and the blue curves are the histogram for the population. And you can look at it and you can see that it's pretty much a bell curve, which is what you expect because it's a large number of data points, and I purposely made it a standard normal distribution. Now if I take this group of 20, these are the 25 data points that I randomly select from my list of 1,000. And if I do a histogram of those 25 data points, kind of like you're doing for your project here, I get the orange graph. So it still looks like a normal distribution. You've got a peak here from 50 to 52, but it's not as near symmetric as it is when you take the larger population. The point of this is, if you take sampling from a really normally distributed population, your samples can look quite a bit different than you might expect. They're not as normal. If you had to make the decision based on the sample, is this a normally distributed? Because it's kind of, there is a criteria, but most of the time you just look at the histogram of the data, the brown curve, and you make some kind of say, yeah, that looks normal. That doesn't sound very scientific, but it is. That's about as scientific as you need. So what I'm going to do is every time I push F9, I'm going to collect another 25 random samples, and it's going to show you how much the sample distribution varies from one sample to another. Oh, okay, why isn't it doing anything? Works. Let's go up to here, data. There we go. Okay. Working with me pushing. Generate a new set of data. But it's not. I wonder what the heck happened here. Maybe when I close my computer and I do it again, it'll be. So I have to go back up here and push F9. So every time I push calculate now, it creates a random set of new data, which still has this relationship. And what I'm going to do is take this and I'm going to make it bigger so you can see the results, what happens. Try to make this thing bigger. Why isn't it? Okay. Well, R stands for regression coefficient. Okay. And the closer that number is to 1, okay, I don't know why that happened. Let's try it again. Okay, so there's my equation. So this is what I would call my regression equation. Y equals 0.8621x minus 2.3885. That's the equation for this straight line. It has a y-intercept of negative 2.38, and the slope is 0.8621. The regression coefficient is 0.8395. So it's not, this is where you see there's more scatter to the data, but you still see this general trend that lower values of x give you lower values of y. And if I push F9 again and create another set of data, where did this go here? Formulas. Here we go. Calculate now. So there's another random set of data, which you'll see this curve doesn't change too much when I randomly select these data. So again, this is the equation for the line that fits through there. In the old days, what you used to do is plot the data points and take a ruler and just kind of estimate. This is what I think it's going to be. Nowadays, because with computers, you can do the calculations. It's reasonably complex to do it, to figure out, based upon what are the x and y values for all these data points, what is the equation. It's not, you actually use calculus to figure out what the equation is, and then use the equation. Once you have that equation, it's just a simple algebraic, big long equation, but it works. And you'll see that the regression equation always fits kind of in the middle of all the data points. Now, one thing I can do to reduce the random nature of the data to make it closer to, so I'm gonna change this formula here. So what I've done now is the data is not quite as random, and if I push calculate now, it's interesting, the equation's not changing. I don't know what's going on today. This should change. It should have not been. So hopefully when I reboot my computer, it'll work again. So something happened. I did this before class. Every time I push calculate now, it should change this equation and r squared, but it's not. So I'll have to demonstrate that next time. Okay. So let me just show you how you do the same thing in Google Spreadsheets. I'll generate another simple set of data. So here's my my x column. That's my independent variable. My y column. And again, I'll just put in some numbers here between 1 and 10. Okay, and then I'll pick some y values that are not exactly equal to those. So let's try 2.1, 4.7, 3.9, 6.8, 9.5, 6.1. Okay, that's all part of my fertile imagination. Now, to do a regression, it's the same kind of deal. You highlight the data, you insert, and you insert a chart. Now, it's going to automatically decide to do a column chart, which is, I don't want that. So one of the choices is scatter plots. Okay, so scatter plots. And so I'm just going to close it for right now, and I'm going to move this out of the way so I can see my data. Okay, and I'll zoom out a little bit. So that looks pretty similar to what we just got out of Excel. We have data points representing the XY coordinates. You can see the trend. As I increase X, Y increases. So the only thing we have to do is figure out how to add a trend line to this graph. So it's not that hard. We could have done it immediately, but we're going to now go back and edit the chart. And if we scroll down somewhere here, customize. Okay. Customize. Let me see if I can find it where it is. Legend, horizontal guidelines. Yeah. Yeah, I also did this just before class too. And it showed me that, gave me a choice to put a trend line on there, but Let me just see what I got here. Let's click there. Okay. What I'm going to do is, let me just delete that. Let me try it again. It might have been when I first inserted the chart and may have given me that choice. So again, I'm going to change this to a scatter plot. And oh, there we go. So you click series and trend line. Okay, so that's all you have to do. You can't use right click. You have to go into customize, series, go down, pick trend line, and there it is. Okay, so now you've got the line. The only thing we don't have is what the equation is and what the correlation coefficient is. You have to do that separately in this particular software, so I'll show you how to do that as well. So the way you do it is you go to, it's one of the add-on features. So under Excel Minor Analysis Tool Pack, one of the choices, we used histogram and we use descriptive statistics. There's also a choice which says linear regression. So what we're going to do is we're going to put in our y values. So I'm going to highlight the y values, click over here. Then I'm going to highlight the x values. Put that in there. So that's the x and y values. And then we have a couple of choices to make. The confidence level, I'm going to take that out of there. Output range. So I'm going to put the output below the graph here. So we'll click on there and we'll put the output range there. And we'll do a line. Well, I don't think we have to do that. I think we just have to do that. So we just put the input range in where we want the output information and say OK. So that's the data. We got a lot more data than we got, but the key thing is, here's the equation. Negative 0.253, that's the x-intercept, and the slope is 1.049. So the equation would be 1.049x minus 0.2. So the data is here, and the r squared is up here, 0.989. So it's not quite as easy to get to, but it's doable using the spreadsheet, the Google spreadsheet. And that's pretty much it as far as scatter plots is concerned. Need to be able to input the data, create a scatter plot, add a regression line to it, and then with the regression line have an equation for the line and the correlation coefficient. And everything else is kind of stuff we don't really need. Okay, so that's it for today about scatter plots. I will come up with an assignment for you. I will create a video that shows you how to do this, and by next Tuesday I think I will be able to give you an assignment related to scatter plots. Then we'll talk on Tuesday, we'll talk about some other topic besides scatter plots.